Hi everyone, welcome to the Concurrency and Domain-Specific Languages preview sessions. Without further ado, I'll introduce Shaz Qadeer from Meta, who will be talking about concurrency. Take it away.
Excellent. Thank you, Samantha. All right, so I'm going to give you a preview of the most important session at POPL 2024, okay? So a couple slides on motivation and then one slide each on each of the 4 papers. So it's a fact that all software, at least all software that matters, is concurrent, okay? And there's a huge variety of these things. So the 2 things that are, close to my heart because of my employment at Meta are distributed systems. So this is a wide swath of software, including compute, elastic compute, storage, databases, caches. This is all the backend systems on top of which Meta's products are built. And then, we're investing a lot on AI training, machine learning. And the distributed, the clusters for doing all this training are also highly distributed and massive compute systems. So there's concurrency at every level. And all this is just in addition to all the classical concurrent systems that we have worried about in the past, such as embedded systems, hardware controllers, multi-core operating systems, runtimes, libraries. These continue to be very critical systems, but additionally, there are new classes of systems that are very critical. So we know that concurrency leads to complexity and difficulty, basically because you need to comprehend and anticipate interactions among different parts of code that are not lexically together. So it creates, complexity in your head, and that leads, you have to invent mechanisms to control these interactions. You don't understand those mechanisms, you don't understand all the interactions. It leads to expensive bugs, which ultimately leads to operational challenges, downtime, loss of revenue, things like that. So it's very important, I think, for the PL community to develop languages, tools, and frameworks to help developers of these systems. And that's precisely what the authors of these 4 excellent papers in this session are attempting to do. So the first paper is a static proof system. So the way I've structured these explanations is that they are like a FAQ, frequently asked questions. So I'll just ask the most obvious question and I'll attempt to answer it. So if you look at the title of the paper, you'll see that there are some keywords there. So what is linearizability? So linearizability is a specification, correctness specification for a concurrent data structure, where you can have fine-grained interleavings among the internal operations of the data structure, but to an observer, to a client, they look like atomic operations, high-level atomic operations. So it would be nice if we could prove this statically. In the past, people have shown that, in general, to have a complete method that will work for all such data structures, you need to have fancy things like prophecy variables and backward reasoning. This paper makes the claim that you can do everything in a complete manner using just forward reasoning, which is nice. Forward reasoning means that, okay, programs have operational semantics that go forward, and you build a proof system that reasons upon forward-going semantics. So it's very natural. So it's more convenient. So that's this paper's contribution. And machine-verified proof means that really there's a tool, a computer-supported tool that's checking the proof. It's not just a pencil paper proof. So that's that paper. This is the next one. This is about on the topic of monitoring. This is specifically predictive monitoring. Monitoring is very easy. There's some kind of specification. You run the program, you collect a trace of it, and then that specification is some kind of a monitor that gets evaluated on that trace. That's what the general area of program monitoring is. Predictive monitoring is a variation on that basic theme. What it tries to do is that it tries to monitor one trace, but by analyzing properties of that trace and of the programs that the trace is coming from, it tries to figure out whether the property, even if it was succeeded on that trace, could have been violated on alternative traces that could be constructed from that trace. So in a way, it's trying to enhance the power of monitoring. For the same amount of work, get more benefit. And then this paper is going to talk about a specific kind of specification language that's called a pattern regular language. So I won't try to explain more on what a pattern regular language is. Okay, the next one, commutativity. So if you attended the keynote this morning, then that whole keynote was about the benefits of commutativity analysis for reasoning about concurrent programs. This paper is another paper in that spirit, and in fact, one of the authors of this paper is the keynote speaker. So I think, is anybody here who did not attend the keynote? Okay, so then you already know what commutativity analysis is, and I don't want to belabor the point how commutativity analysis helps with proofs of programs. Maybe I can tell you what is a parameterized program. Parameterized program is a formal model of a concurrent program in which you have a piece of code that is parameterized by a process ID or a thread ID. So in addition to global variables and local variables, it can access a parameter. And then the idea is that you have an unbounded number of copies of that same code running, each with a different process ID. And you try to prove properties of this or in this model. All right. Last paper is Coarser equivalences for causal concurrency. So here you will get to hear about trace theory, specifically Mazurki-Witch trace theory. So what's going on here? So remember I was talking about traces of concurrent programs. So Mazurki-Witch trace theory is a theory about such traces extended with a notion of a symmetric relation that is thought of as commutativity. So from a given trace, by reordering adjacent events that satisfy the commutativity relation, you can generate lots of other traces that are supposed to be equivalent. So Mazurki-Witch trace theory studies such things. So there's a rich theory here, and it tends to be parameterized in 2 dimensions. You can change the definition of the commutativity relation, and that can create different kinds of trace families. Or you can also ask different questions about these traces. So this paper is a foundational paper. It's a theoretical paper in that space that is playing in this area where they are changing various aspects of the commutativity relation and also asking different kinds of algorithmic questions. Okay, that's all.